Hello everyone. In the previous video we studied about the SCR. What are all the what are all the layers? How many layers are present in it? And we also studied its characteristic, and we also studied the operating principle of the SCRs. Now, in that we came to know that in that we came to know So we studied about, we came to know that once we turn on the SCR, it is, and in the on state, it cannot be turned off as by controlling the gate voltage. That is, if we make a gate voltage as equal to 0, my SCR will not turn off. So this is what is the this involves a principle of turning of the SCR. So let us study how to turn off the SCR once it is turned on, right? So turning off an SCR, that is when the SCR is in the conduction mode, the gate is ineffective in turning it off. The turn off mechanism, whatever the turn off mechanism we are going to incorporate, that is called as commutation, and it can be achieved in two ways. One is the natural commutation and the other one is the forced commutation. The natural commutation is going to happen when we make our Vg as equal to 0. That is, the gate voltage is, if we make it as equal to 0, then such a kind of natural commutation we call it as natural commutation. This can happen when the source that feeds the current to anode of SCR turns off to a zero current. This is the case when SCR is fed from an AC source. In this situation, the commutation is known as the line commutation. Okay, but when we go for the forced commutation, in this method, the current to SCR is forced, right? The current to SCR is forced to become zero by passing a current through in opposite direction from an independent circuit. Now, what we are going to do in the forced commutation is, here we are going to induce another current which is flowing in the opposite direction of the SCR current, such that both the currents get neutralized and the SCR will be going to turn off. In order to do this, we should possess a special circuit for this. In order to achieve the forced commutation, we should possess a special circuit for this. Whereas in the natural commutation, just by making Vg as that is the gate voltage as equal to 0, we can achieve the natural commutation. But as such, when we make our gate voltage as equal to 0, but we cannot turn off the SCR practically. So this natural commutation is also called as a line commutation. Okay, so turning off the SCR is called commutation. We have two kinds, natural and forced, right? So let us look into the forced, how the forced commutation is going to happen. In the forced commutation, you can we are going to consider one transistor, one external voltage, and the SCR. So this is what is the SCR. Now, once the SCR, what is our principle, or what we have to adopt here is, I should make sure that my SCR should turn off, right? So how to make this turn off? It is by using the forced commutation we are taking it. Now, how to make this? We have connected a transistor and a DC battery source in series, which in series with the SCR, and it is as shown. When the SCR is in the conduction mode, yes, when the SCR is in the conduction mode, that is on state, my base current, whatever the base current that is there, that would be equal to 0. When the transistor is off, it is almost an open circuit. So that is what is off, right? To turn off the SCR, a positive base current of the transistor IB. So whenever the SCR is in the on condition, we should make sure the base current of the transistor should be made equal to 0. And when we want to turn off the transistor, we are going to give an external external voltage to the transistor. As a result, the base current is going to flow across this transistor, right? So positive base current pulse of magnitude. That is, in order to generate voltage across this transistor, we are going to use one pulse generator. So whenever SCR is in the on condition, the pulse generator should not generate any pulse, making the base current as equal to 0. Whenever I want my SCR to turn off, the pulse generator should generate a pulse such that there is a current across the IB. Now, the transistor is now going to act as a short circuit, causes a very large current I off through the SCR in opposite direction. That is, the current is constituted from the transistor. So we can see the transistor current is going to be in the opposite direction of the SCR current. Once there is a flow of current from the transistor in the opposite direction of SCR, we can say the current is going to get cancel each other. The total SCR current reduces to 0 in a very short time, which will cause the SCR to turn off. So that is what is shown here. So the T on refers to the turn on time of the SCR or the thyristor, and T off refers to the turn off time of the SCR or the transistor. The transistor has to withstand large current, but for a short time. Turn off time of an SCR is equal to it takes almost 5 to 30 microseconds to turn off a SCR. So we know a silicon controlled rectifier is also called as a thyristor, right? So it is going to withstand a high temperature. So as a result, we call this as a thyristor. So in the forced commutation, we come across for the forced commutation, we are using along with the SCR, we are going to use an external transistor, an external voltage, and a pulse generator. For this, once the SCR is in the conduction mode, my pulse generator should not generate any pulse. That is, while in the T on, it should not generate any pulse to the transistor is given. Once I want the SCR to be turned off, I make sure that the pulse generator is going to generate a pulse and my SCR is going to be turned off. Okay, why this is going to get turned off? Because there is a current from the transistor I off which is in the opposite direction to the flow of the SCR current. As a result, that is the SCR, which makes the SCR current to reduce to 0. So this is about the forced commutation, how the forced commutation is occurring in the SCR. Now let us look into the SCR characteristic curve. What actually is going to happen in the SCR characteristic curve? So what is we already know a characteristic curve represents a plot of current versus voltage. Once we come into this, we can see that our SCR works in 4 different regions. Yes, the SCR works in the 4 different regions. One is the forward breakover voltage. Another one is the holding current, forward and reverse blocking current or the blocking regions, and reverse breakdown voltage. Now let us look into forward breakover voltage, which is given by VFBR. Forward breakover voltage, it is the voltage at which the SCR enters into the conduction region or the conduction mode. This voltage reduces as gate current increases, right? So forward breakover voltage, that is forward breakover voltage is this one, VF3, VF2, VF1, VF1. So these are all the forward breakover voltage, whereby SCR starts conducting. That voltage we call it as the breakover voltage, right? So and VFR has a dependence on the circuit between the gate and the cathode terminals of IG. Now let us go for the holding current IH. Now what is this holding current IH? So you can look here in the graph, IH is marked here. IH says that it is the value of current below which SCR switches from conduction state to forward blocking region. So what is happening here? So IH is the holding current wherein which the holding current IH is a holding current where this current it is the current below which the SCR switches from the conduction to the forward blocking region under the steady state conditions. This is called your holding current, right? So it switches from, that is, the holding current is the region where the SCR switches from the conduction mode to the forward blocking region, right? The SCR switches from the forward blocking regions. Now, what is this forward and reverse blocking regions? So those are the regions in which SCR is open circuited and no current flows through this. So this is your forward blocking region, forward and reverse blocking regions, where no current will flow across this region. We can say exactly that the current would be equal to 0. Now, reverse breakdown voltage. So what is this reverse breakdown voltage? It is the reverse anode to cathode voltage at which the Zener or the avalanche region of a diode is avalanche breakdown is going to happen, or that is going to take place in this region. So these are the characteristic curve of a, this is the characteristic of a SCR. So totally it has 4 regions. One is the forward breakover voltage, next is the holding current, and forward reverse blocking region, forward and reverse blocking regions, reverse breakdown voltage. For the forward breakover voltage, it is the voltage where the SCR enters into the conduction mode, and it holding current is the current which is responsible for of the SCR to switch from the conduction mode to the forward blocking regions, switch from the conduction mode to the forward blocking regions. Forward and reverse blocking regions are the regions that corresponds to the SCR where it enters into the open circuit conditions where no current flows across this, and we have the reverse breakdown voltage where the SCR enters into the Zener or the avalanche breakdown condition. So this is the characteristic curve of your SCR. So this, we can see in the graph the as and when the forward breakover voltage is increased, that is VF1, VF2, VF3, as and when the forward breakover voltage is increasing, the gate source voltage is going to in her IG3, IG2, IG1, it is also decreasing. So as a result, that is when Ig1 is equal to 0. So look into the curve, as and when it is increasing, as and when the voltage is decreasing, the Ig3, that is the gate voltage, is shifting and it is almost becoming 0, right? So once more and more when VGF is equal to 0, we can expect it to be the voltage to be 0. So this is about the SCR characteristic. So let us study the effects of a gate current. So what is happening here is we have a V1, V2, V3. So V1 is lesser than V2. V1 is greater than V2 and V2 is greater, V3. So this is about your breakdown voltage VBO, where my gate current is equal to 0. So as and when you look into this, when V1, as and when the V1 is greater than V2 and V2 is greater than V3. So what is going to happen with respect to your current voltages Ig3, Ig2 and Ig1 is the inference about the VI characteristic of SCR showing effects of varying the gate current. Okay. So once we have done with this is the characteristic curve of SCR. Hope this video is beneficial for you. Thank you for visualizing this.